Hi class, in this video I'm going to go over how to do a finite element analysis to study the deflection of your drone under a loading scenario. The loading scenario that we're going to be giving is that we'll have 0.2 newtons applied on each of the drone propellers. What this is a 20-gram mass on Earth force. Why we're doing this is we can expect our drones will be anywhere from 10 to 20 grams, and what we'd like is that each propeller actually on its own has the capability to lift our drone. And so what this basically simulates is 4 times the load we should expect our drone to be experiencing. And our criteria for it to be stiff enough would be that under that load, it's not deflecting more than 100 microns. So what I've modeled in here in this design, and this isn't a correct design by any means, it's just a random design I made. So please don't be influenced on this design and say that, oh, I should design my drone to look like this. This is just kind of something random I came up with. Anyways, what I have here is a testing jig, and what this would simulate, if you look at it from the side and we pushed up on this both propellers, it's kind of like a 3-point bend test. And so these are actually like roller contacts. So if you're familiar with statics, we could consider these as roller constraints where the drone chassis would touch these bars. Okay, so to make a finite element simulation, I think the first thing you want to do is go ahead and modify your physical material and make sure that your bodies, so the body here I have is the drone body. Make sure you assign the correct material. So the material we'll use is ABS. So go ahead and assign that, step 1. And then you can go ahead and go into the simulation environment. So once you're in the simulation environment, it's going to ask you which kind of study we're going to want to do. And so for this case, what we're going to want to study is a static stress. So we'll be simulating a static loading scenario and essentially treating our drone as a cantilever beam. So go ahead and click on the static stress analysis and then click create study. And what you should see is your drone chassis as a body. But before we go ahead and do this study and do the entire drone, what you want to do is take advantage of any symmetry. And you always want to do this when you're studying finite element analysis to simplify your analysis. So what we can see here is I've actually got quarter symmetry. So there's 2 planes of symmetry. There's not 3. So if you look this way, I don't have a symmetry across the XZ plane, but I have symmetry across the X or the XY and the ZY. So go to simplify. And once you're in simplify, what we want to do is go ahead and make a sketch. You can make it on the XZ plane. And what we'd want to do here, go ahead and use the line tool. It doesn't have to be a fully constrained sketch. We're just kind of roughing out. What we want to do is preserve a quarter, or actually cut a quarter away. So go ahead and make this perpendicular to that. And now, once you stop your sketch, what you can go ahead and do is extrude that all the way through. And you could say all. So you, and I better go 2 directions. So better edit this extrude, edit feature, go 2 sides, and let's go ahead and make that second side to all. Okay, and what you'll see, what I've done here is I've actually just left myself with a quarter of the model, and so it should react the same. But now this will change my boundary conditions a little bit, so let's talk about how to do that. When you cut through a body and it's contacting another body, what you need to do is set up the constraints so that your model knows that it's connected to itself here. And essentially any plane that you're using to cut through, that body can have a shear force and it can exert a moment force on that face. So the appropriate constraints is not fixed. We're not going to fix this face because what that would simulate is if you were clamping down really hard on that face. That's not what's going on. The other body, it may bend and expand and contract with its own self. So what it can resist is a moment. So if you set up a frictionless constraint on the faces that you cut through, that will properly simulate that. Okay. What this frictionless constraint will do is if I'm applying it to an XY face, so you can see this is my XY face, it will let it move anywhere in the XY face, but it won't let it rotate about the Z axis or the Y axis. It can rotate about the X axis, and it will not let it translate perpendicular to the face. So if it's in the ZY plane, it won't be able to move up. It won't be able to move up off of that plane. So it couldn't move like that. But it can move left to right and up and down. Same thing with the roller constraints that we've applied to the XY face. We're still not done how we're applying the constraints because what we need to model is the bar, and where the bar contacted was the actual planes that we cut. So in theory, if it's modeled as a point contact, we want to make sure that it will constrain it just as that bar would. And what the bar would do is it would allow it to, it could not resist a translation in the X or the Z, but what it would allow us to do is resist a translation in the Y. If you go to constraints and go fixed, I've already selected that edge, but let me unselect it and then reselect it. So I'm constraining this edge, but the only axis I need to constrain it, and that's going to take any node that's along this edge and constrain it. So we actually just need the Y, and we can apply that to two different edges. So we just need to constrain those in the Y. Okay. Okay, so now that I have appropriate boundary conditions to simulate both the bar that we would be testing this on and then the symmetry planes that we've cut through, we can go ahead and apply our structural loads. So you go to loads, and we're going to apply it as a force and apply it to any face, and ideally it's a face that is large enough so it's not a point contact. So you wouldn't want to apply it to just one edge because that will affect your solution. And in fact, having just this edge right here being a constraint will make the solutions around that constraint not very trustworthy. However, the farther you get away from the constraint, the solution should get better. And that's actually a principle called St. Venant's principle that says the further you go away from a constraint, the better your solution will be. So let's go ahead and apply this as a vector load. And the vector direction is I'd be pushing up on this. So I'm going to go ahead and push up with 20 newtons, or 0.2 newtons. So go ahead and apply that load, and what you should see is a little force arrow. The next step here is to go ahead and, under the Solve tool, go ahead and generate a mesh. So once you get your mesh, you can actually go under the Solve tool and go for Solve Details, and it'll tell you your mesh. So what we have is 11,301 tetrahedral units, and that's making up our mesh. And you'll see we can actually, this is a lot of units. So one thing that you may consider doing is actually it's adding extra meshes to capture this geometry or this tight little radii. And in reality, that's probably not going to affect the deflection over here where I've got my motor casing or motor housing. So that is something I could try to simplify to make this model run faster and actually even give you a better solution. But I'm going to go ahead and proceed with this mesh. The next thing you want to do with your study is verify under material that your material properties are correct. So it's ABS, and that's good. Where if you could see the properties, you go, let's click on our ABS. And what you may do is you may want to change these if they don't match with your actual given one. But we'll go ahead and assume, and this is a big assumption here, is that our material is going to behave isotropically. Now, when you 3D print, you're laying down fiber by fiber, and this is probably not a very good assumption, but at least we'll be able to use this as a comparative analysis between different designs. So we may not get a exact solution, but we could compare designs. So if one design is stiffer than another using the same material, we may feel confident that that design is better. Okay, so under your study, if you right click on that, go to settings, and under the settings, what we want to do, go to advanced settings, make sure your mesh is parabolic mesh. That should give you a better solution. And then we want to go to adaptive mesh refinement and change this to a custom refinement. And then what this is going to do is if it's going to do a solution, refine the mesh, solve it again, and then check its solution to see if it's converging. And you do want to make sure it's converging. And since we're going to be studying deflection, the convergence criteria that we want to take a look at is the total displacement. So go ahead and click OK. So now that we've got the proper materials, the proper constraints, the proper mesh, and the right loads, we can go ahead and solve. So click the solve button, and what it'll tell you is that it's solving it on the cloud. So, and this actually happens very fast for Fusion. And now that it's finished solving, it's telling you that it has a safety factor of 15, and they're using the von Mises criteria. Now, we knew that it shouldn't be failing because our drones aren't failing under their own weight, but we're not even studying this for in terms of safety factor. We're interested in deflections. Go ahead and hit close, and then close, and then you're visualizing your solution. One thing that's actually nice to see is the mesh. And if you show the results, you can turn on the mesh. It's kind of nice so you can see the mesh at the same time. Now what we want to do is plot the displacement, and the displacement, not the total displacement, the displacement in this case, it's in the direction you apply your load. So for my model, I want to see the displacement in the y direction. Okay. And what you'll see here is that I'm well under my, now this is a grossly exaggerated view. That's one thing to know, that I've exaggerated the deflection. So if you go to results, deformation scale, if you do actual, what you'll see is there's almost no visible deflection. Now, what you can do under results is make it a smaller deflection. So this is showing you that it's exaggerated so you can kind of conceptualize what the deflection is. Okay, so there's my results. What I would know from this is that basically I have met my design criteria. One thing to check is that your solution converged, so you should be getting some convergence. And it looks like even in one solution step, the error was smaller than the 5%, so they went and stopped. You may actually force it to make more runs just so you can guarantee, but here it was enough for it to converge in just two solution steps. Okay, so that's how you'll model your finite element analysis for your project.